In this lesson, we introduce very important equations to us. We are going to have our constant acceleration equations for rotation, and we have our equations that relate our tangential to our angular quantities. So first, the red boxed equations that I have shown here. These are the equations that relate our tangential motion, right, V, alpha, and arc length distance delta s, all tangential, all linear concepts, to the rotational motion that occurs along the circular arc of the wheel at a position R, R, and R. What is most important about these equations, one, is that we have them memorized. V tan equals omega R, A tan equals alpha R. But if you are going to use them, when you use them, please get this in and highlight it however you highlight it. I got my big splashy splash here. Must have omega in radians per second and alpha in radians per second squared for those equations. Now, the derivations, the conversion from the linear to the angular is very easy now that we have our equations to transform between the two. So with these transformation equations between the linear world and the angular world, we can go from our linear equation to our angular equation simply by substituting in, and notice the r's all cancel out. Cancel, cancel, cancel. And please put in that they are vector quantities, because in our linear case, make sure you get this in here, you must have the positive or negative in there for the vector quantities. And now we must have the positive and the negative in there for counterclockwise and clockwise, and that's by convention. We'll talk more about the convention in another page of notes or so. But this is really important. So we're always going to be looking at the plane of the page, and when rotating in the plane of the page, if the wheel is rotating counterclockwise, that is going to be positive. If the wheel is rotating clockwise, that is going to be negative. And again, when we talk more about that convention, you'll have an easy way to remember it. All right, I have another splashy splash over here in pink. So I'm not going to just run through all the algebra for you. Please take a moment and look to see how our, x final equals x initial plus v initial times time plus 1/2 at squared. When we substitute in these transformations from our tangential to our angular, becomes theta final. So still, position final. Theta position final equals position initial, theta initial, plus velocity times time plus 1/2 acceleration times time squared. Conceptually, we would say them the exact same way. And then, of course, we have our third constant acceleration equation. And for rotations, we absolutely will be looking at the fact that since the velocity vector final equals velocity vector initial plus acceleration times time is a linear equation, that you can just get the average value, since it follows a straight line, right? The average value will just be this one plus this one divided by 2. It'll give you the one right in the middle. So if you have omega as a function of time for constant angular acceleration, this allows us to do the initial plus the final divided by 2. And my splashy splash over here, to get back to that, please make sure that you put down in your notes these equations. If the problem, the homework question that you're looking at, has everything in revolutions per second, you can leave it in revolutions per second, right, for omega, revolutions per second for omega, and as long as alpha is in revolutions per second squared, you can leave it in revolutions, and I recommend that you do. You cannot mix or match units, however. So revolutions and radians we can't mix and match, and we certainly can't mix and match like seconds, minutes, hours. Everything has to be consistent. So please make sure you get down all the annotations that you want off of this page of notes, and we'll be practicing doing some constant acceleration equations for rotation, but not too much because we've already played this game and it's pretty much plug and chug as we have done with our linear cases.